Welcome to Cosmos in a Pod Space and Astronomy series. Today we're diving deep into something truly awe-inspiring. Stellar nurseries. The vast cosmic clouds where stars are born.
It's amazing to think that these seemingly empty regions of space are actually the bustling cradles of stars.
Right, it's like a cosmic paradox, something so cold and dark giving birth to the fiery giants that we see in the night sky. So help me understand this. What exactly are these stellar nurseries made of?
They're also known as giant molecular clouds, or GMCs, and they're primarily composed of cold gas and dust. The key ingredient here is molecular hydrogen. It's the basic building block for star formation.
Okay, so these clouds are essentially massive reservoirs of hydrogen. But how massive are we talking? Are these things bigger than our solar system?
Oh, much bigger. Think tens to hundreds of light years across. For perspective, the Orion Nebula, one of the most famous stellar nurseries, is about 24 light years across. That's thousands of times larger than our solar system.
Wow, that's hard to even fathom. And you mentioned they're cold. How cold is cold in the depths of space?
Think natixion's 260 degrees Celsius, or I to the 440 Fahrenheit. That's barely above absolute zero. And that extreme cold is crucial because it keeps the hydrogen molecules from breaking apart. If they were warmer, they would have too much energy and wouldn't clump together.
That makes sense. It's like they need to be chilled out to get the star-making process going.
Yeah.
So we've got these giant freezing clouds of hydrogen just hanging out in space. What actually kickstarts the process of star formation within them?
It's this fascinating interplay of forces. Gravity, of course, is the main sculptor, constantly pulling gas and dust together into denser clumps. But it's not a solo act. Other cosmic events can either trigger or accelerate the formation of these stellar nurseries.
Like what else is going on out there that can jumpstart star birth?
Imagine a supernova, the explosive death of a massive star. The shockwaves from that explosion ripple through space, and when they encounter a nearby cloud of gas and dust, they can compress it, kind of kickstarting the process of star formation.
So a star's death can actually lead to the birth of new stars. That's poetic and kind of mind-blowing.
It is, isn't it? The universe loves to recycle. And it's not just supernovae, galaxy collisions. Those massive cosmic events where galaxies quite literally smash into each other can also do the trick. These collisions cause gas clouds to get squeezed together, triggering intense bursts of star formation.
Wow, that paints quite a dramatic picture. It's like a cosmic demolition derby leading to a baby boom of stars.
Right.
Are there any other more subtle forces at play?
Even the spiral arms of galaxies themselves have a hand in this. You see, these arms create something called density waves. Imagine a cosmic traffic jam, where gas and dust bunch up, creating zones of higher density. These areas become prime real estate for star formation.
So it's not just random chance. It's like the galaxy itself is setting the stage for these stellar nurseries to form. But okay, so we have a nursery primed for star birth. What's the next step? How do actual stars emerge from this swirling cloud of gas and dust?
Think of it like a cosmic recipe with specific steps. First, you have fragmentation. That giant cloud breaks up into smaller clumps, each with the potential to become a star or maybe even a whole cluster of stars.
So it's like a giant cloud giving birth to smaller star-forming clouds. What happens within those smaller clouds?
Within each of those fragments, gravity takes center stage again, pulling gas and dust inward to form a hot, dense core. This core is what we call a protostar, basically a star in its embryonic stage.
So the baby star is starting to take shape. What happens next? Is it just a waiting game for it to grow bigger?
Not quite. As the protostar grows, gas and dust start swirling around it, forming what we call an accretion disk. This disk acts like a cosmic buffet, funneling more and more material onto the growing protostar.
So it's like a whirlpool pulling everything towards the center, making the protostar bigger and bigger.
Exactly. And as this happens, the core of that protostar gets hotter and denser. Eventually, it reaches a critical point where the pressure and temperature are so high that something amazing happens. Hydrogen atoms start fusing together to form helium.
Wait, is that what we call nuclear fusion? That's what powers stars, right?
Yes, it's nuclear fusion. It's the moment of truth, the grand finale of this stellar recipe. The fusion of hydrogen into helium releases an enormous amount of energy, and boom, a star is born.
That's incredible. It's amazing to think those tiny atoms fusing together are what makes stars shine.
Mm-hmm.
But what happens to all the gas and dust that was swirling around the protostar? Does it just stay there?
Not at all. The newborn star, full of energy, starts to flex its muscles. It blasts out radiation and powerful stellar winds, which clear away the remaining gas and dust. Imagine it like the star is clearing its own space, announcing its arrival to the universe.
So it's like a cosmic coming out party, the star finally revealing itself in all its glory.
Precisely. And from that point on, the star embarks on its long journey, shining for millions or even billions of years.
Wow, what an incredible journey. From a cold, dark cloud to a brilliant star lighting up the cosmos. It's like a testament to the awesome power of the universe.
It truly is.
That's
But we've
all.
only just begun to scratch the surface of these stellar nurseries. There's so much more to explore.
This is already so fascinating. I can't wait to learn more.
Well, buckle up because there's a lot more to uncover.
Great, but before we go any further, I think we need to take a little break. Don't worry, we'll be back soon to continue our deep dive into the fascinating world of stellar nurseries.
Welcome back to Cosmos in a Pod.
Okay, I'm ready to dive back into the world of stellar nurseries. That was some seriously mind-blowing stuff.
It's just the tip of the iceberg. Last time, we talked about what stellar nurseries are and how they form. Now let's zoom in and look at the different types of these cosmic cradles.
Types. I thought a giant cloud of gas and dust was a giant cloud of gas and dust.
Not quite. It turns out stellar nurseries come in a variety of flavors, each with its own unique characteristics. We touched on them briefly before the break, but there are 4 main types: dark nebulae, emission nebulae, reflection nebulae, and HII regions.
Good, that's a lot to unpack. Let's start with dark nebulae. Those sound kind of ominous.
They do have a certain mystery to them. Dark nebulae are essentially dense clouds of gas and dust that block light from anything behind them. Think of them like cosmic silhouettes against the backdrop of the Milky Way.
So they're dark because they're so thick that light can't get through.
Yeah.
That makes sense.
Exactly. The dust grains within these nebulae are particularly good at absorbing and scattering light, making them appear dark to us. One of the most famous examples is the Horsehead Nebula, which gets its name from its iconic horsehead-shaped silhouette.
I've seen pictures of that. It's amazing how these dark clouds can create such distinct shapes.
Yeah.
But if they're so good at blocking light, doesn't that make them difficult to study?
It can be challenging, but it also makes them incredibly important for star formation. Because they're so dense, gravity has a stronger pull in these regions, making it easier for the gas and dust to clump together and form stars.
So in a way, the darkness itself is what allows stars to be born. That's kind of counterintuitive.
It is, and it's why we often refer to these dark nebulae as the hidden nurseries of the universe. But let's shift gears and talk about something a bit more vibrant: emission nebulae.
Ah, yes. These are the ones that glow in those incredible colors, right?
You got it. Unlike dark nebulae, emission nebulae are lit up by the intense radiation of nearby hot, young stars. These stars emit ultraviolet radiation, which ionizes the hydrogen gas in the nebula, causing it to glow.
Ionized. So the radiation is stripping electrons from the hydrogen atoms?
Precisely. And when those electrons recombine with the hydrogen atoms, they release energy in the form of light, which is what gives the nebula its characteristic glow.
That explains all the reds, blues, and purples I've seen in pictures of nebulae.
Exactly. And it's not just a visual spectacle. The different colors actually tell us about the elements present in the nebula. Different elements emit different colors of light when ionized, which is why we see such a variety of hues in emission nebulae.
It's like a cosmic neon sign, advertising the ingredients of the universe.
I like that analogy. And speaking of spectacular sights, the Eagle Nebula, with its famous Pillars of Creation, is a prime example of an emission nebula. Those towering pillars you see in those iconic images are actually columns of cool gas and dust that are being sculpted by the radiation from nearby massive stars.
Those images are just breathtaking. It's amazing how those stars can shape the nebula like that.
It's a testament to the incredible power of these stars. And the colors in the Eagle Nebula are truly stunning, with reds from ionized hydrogen, blues and greens from oxygen and sulfur, and so much more.
So we've got dark nebulae hiding star formation and emission nebulae glowing brightly. What about reflection nebulae? Those sound a bit more subtle.
You could say that. Reflection nebulae are like cosmic mirrors. They don't emit their own light like emission nebulae. Instead, they reflect the light from nearby stars.
So the starlight is bouncing off the dust particles in the nebula.
Exactly. And here's the interesting part. Blue light scatters more efficiently than other colors. That's why reflection nebulae often appear blue to us. The Pleiades Nebula, for example, is a beautiful example of this.
I've heard that one. It's a cluster of stars, right?
Yes, a cluster of young, hot stars surrounded by a faint blue nebulosity, which is simply the starlight reflecting off the surrounding dust. It's like they have a cosmic halo.
That's a great image. And do reflection nebulae ever hang out with emission nebulae? Could we see both types together?
Absolutely. They often coexist, creating these stunning combinations of glowing gas and reflecting dust. It's like a cosmic tapestry of different colors and textures.
Okay, that leaves us with one more type. HII regions. Are those similar to the ones we've already talked about?
They are related to emission nebula, but they're unique in a few ways. HII regions are specifically large clouds of ionized hydrogen surrounding extremely hot young stars. These stars are so hot that they emit vast amounts of ultraviolet radiation, which ionizes the surrounding hydrogen on a massive scale.
So it's like an extreme version of an emission nebula. Supercharged, so to speak.
That's a good way to put it. And these HII regions are critical players in the evolution of galaxies. The radiation from those hot young stars can actually trigger the formation of new stars in nearby gas clouds, continuing the cycle of starbirth.
Wow, so it's like a chain reaction of star formation rippling through the galaxy.
Precisely. And in addition to sparking new stars, HI regions also create these amazing structures within galaxies, like bubbles and filaments. This is caused by the radiation and stellar winds pushing against the surrounding gas and dust.
It sounds like a cosmic battleground, with stars shaping the very structure of the galaxy.
It's a dynamic and ever-changing environment, that's for sure. And the Orion Nebula, which we mentioned earlier, is a prime example of an HII region. It's a giant cloud of ionized hydrogen surrounding a cluster of hot young stars, showcasing the raw power of stellar birth.
Okay, so we have these four main types of stellar nurseries, each with its own unique characteristics and role to play. It's amazing how diverse these cosmic cradles can be.
It really is. And studying these different types helps us piece together the complex story of star formation. Each one offers a unique window into this incredible process, allowing us to better understand the interplay between gravity, gas, dust, and starlight.
It's like having different pieces of evidence that help us build a more complete picture.
Exactly. And by studying these nurseries, we're not only learning about the birth of stars, but also about the evolution of galaxies and the universe as a whole.
It's all connected, isn't it? From those tiny dust grains to the largest structures in the universe.
It truly is. And that's the beauty of astronomy. It's a constant reminder of the interconnectedness of everything.
This is all so mind-blowing. I feel like we've been on a whirlwind tour of these cosmic nurseries.
We've covered a lot of ground, but we're not done yet.
There's more. I'm on the edge of my seat.
Now that we have a good understanding of the different types of stellar nurseries, let's delve into some of the amazing discoveries astronomers are making within them.
Discoveries? You mean there's even more to learn about these already fascinating places?
Oh, absolutely. Astronomers are constantly pushing the boundaries of what we know about stellar nurseries, using cutting-edge telescopes and techniques to unveil their secrets.
Okay, I'm all ears. Tell me everything. What are some of the most exciting things they're finding?
Well, one area that's really hot right now is the study of protostars. Those baby stars just beginning to take shape.
Right, we talked about those earlier. They're like the embryos of stars, still in the womb of the nebula.
Exactly. And thanks to powerful telescopes like the James Webb Space Telescope, astronomers are now able to observe these protostars in unprecedented detail.
So we're getting a much clearer view of those early stages of star formation.
Absolutely. We're seeing the accretion disks around protostars, those swirling disks of gas and dust that feed the growing star. It's like watching a star being built right before our eyes.
That's incredible. What else are we seeing?
We're also observing jets of material shooting out from the poles of these protostars.
Jets. What are those?
Imagine these powerful beams of gas and dust being ejected from the protostar as it spins. They're like cosmic geysers, spewing material out into space.
Wow, that sounds intense. Why do they do that?
These jets actually play a crucial role in regulating the growth of the protostar. They help to carry away excess angular momentum, which prevents the protostar from spinning so fast that it tears itself apart.
So it's like a safety valve, keeping the star formation process under control.
Exactly. And these jets can extend for light years, carving out cavities in the surrounding gas and dust, creating these amazing structures within the nebula.
It's like a cosmic sculpture at work, shaping the nebula with these powerful jets. What else have astronomers discovered?
Another area where they're making incredible progress is in the study of massive star formation.
Right, those are the behemoths of the stellar world, the ones that live fast and die young.
Exactly. And forming a massive star is a much more dramatic and energetic process than forming a smaller star like our sun.
How so? What makes it so different?
Well, massive stars form much faster and burn much hotter. They exert a tremendous influence on their surroundings, blasting out intense radiation and powerful stellar winds that can carve out huge cavities in the surrounding gas and dust.
It sounds like a cosmic hurricane, wreaking havoc in the nebula.
It's a chaotic and violent environment, and astronomers are using sophisticated computer simulations to try and understand how these massive stars form and how they impact their surroundings.
So it's like a cosmic detective story, piecing together the clues to figure out how these giants are born.
Precisely. And one of the key questions they're trying to answer is, how do massive stars manage to accrete so much material so quickly?
Right, because they need a lot of fuel to grow so big so fast.
Exactly. And it seems that magnetic fields might play a key role. Astronomers are finding evidence that magnetic fields can help to channel gas and dust towards the growing massive star, accelerating its growth.
So it's like a cosmic funnel, directing material towards the star and helping it grow into a giant.
That's a good way to think about it.
Yeah.
And another exciting discovery is that massive stars often form in clusters.
Clusters, like groups of stars all born together.
Precisely. Astronomers are finding that massive stars rarely form in isolation. They tend to be born in these bustling stellar nurseries where multiple stars are forming simultaneously.
So it's like a cosmic nursery full of baby stars, all growing up together.
Exactly. And this makes sense because the conditions that favor massive star formation, like high gas density and strong magnetic fields, also tend to be present in these clustered environments.
So it's like a perfect recipe for creating a whole bunch of stars at once.
Exactly. And studying these star clusters helps us understand the dynamics of star formation on a larger scale. It's like zooming out and seeing the bigger picture of how stars are born.
It's fascinating how we can learn so much about the universe by studying these stellar nurseries. But wait, you mentioned earlier that massive stars have a big impact on their surroundings. Can you elaborate on that?
You're talking about feedback, the way that stars influence their surroundings and how those surroundings in turn influence star formation.
Right, that two-way street we talked about before.
Exactly. And astronomers are finding that feedback plays a crucial role in regulating star formation. For example, the radiation and stellar winds from massive stars can heat up and disperse nearby gas clouds, preventing them from collapsing and forming new stars.
So those massive stars are like cosmic bullies, pushing around the smaller guys and preventing them from growing.
In a way, yes, but it's not all bad. The shockwaves from supernovae, the explosive deaths of massive stars, can actually trigger new star formation by compressing nearby gas clouds.
So it's like a cosmic cycle of life and death, with the death of one star giving birth to new ones.
Precisely. And understanding this feedback loop is key to understanding how galaxies evolve over time.
It's like a cosmic dance, a delicate balance between creation and destruction, all playing out in these incredible stellar nurseries.
That's a beautiful way to put it. And these are just a few of the many exciting discoveries that astronomers are making in stellar nurseries. With new telescopes and technologies coming online all the time, we can expect even more groundbreaking discoveries in the years to come.
It sounds like this field is constantly evolving, with new discoveries being made all the time.
It is, and that's what makes it so exciting to be a part of. There's always something new to learn, something new to discover.
This has been an incredible journey so far. But before we wrap up part 2, are there any particularly mind-blowing discoveries that you've come across in your research? Anything that really stood out to you?
There are so many to choose from, but one that always sticks with me is the discovery of organic molecules in stellar nurseries.
Organic molecules. Wait, are we talking about the building blocks of life?
Exactly. Using radio telescopes, astronomers have detected complex organic molecules like alcohols, sugars, and even amino acids in the gas and dust surrounding young stars.
Whoa. So the ingredients for life are already present in these stellar nurseries.
It seems so. And this has profound implications for our understanding of the origins of life in the universe. It suggests that the seeds of life may be widespread, sown throughout the cosmos.
That's incredible. So those twinkling stars we see at night might be harboring the potential for life on other planets.
It's a tantalizing possibility. And it highlights the fact that we're not just studying stars and galaxies, we're studying our own origins.
It's like we're looking back in time to the very beginnings of everything.
Exactly. And that's what makes astronomy so captivating. It's a journey of discovery, a quest to understand our place in the universe.
Well said. And on that note, we'll delve deeper into the mysteries that still surround stellar nurseries and the unanswered questions that keep astronomers searching for answers after a quick break. Welcome back to Cosmos in a Pod.
We're in the final stretch of our deep dive into stellar nurseries.
It feels like we've traveled light years in just a few minutes.
We have covered a lot of ground. We've gone from those immense frigid clouds of gas and dust all the way to the birth of dazzling stars.
And we even touched on the mind-blowing possibility that the ingredients for life might be sprinkled throughout these stellar nurseries.
It really makes you wonder what else is out there waiting to be discovered.
Speaking of discoveries, I'm curious about the mysteries that still surround stellar nurseries. What are some of the big unanswered questions that astronomers are grappling with?
There are so many, but one of the most fundamental questions is, what determines the mass of a star? Why are some stars colossal giants while others are relatively small, like our sun?
It seems like a pretty basic question. Wouldn't the amount of material a star has access to determine its size?
It's not quite that simple. While the amount of gas and dust available certainly plays a role, we're still unraveling the mechanisms that regulate the accretion process. What we don't fully understand is what determines how much material a star can actually pull in before it stops growing.
So there must be some sort of cosmic brakes that prevent stars from just growing infinitely large.
Exactly, and that's what we're trying to figure out. One intriguing theory is that feedback from the star itself plays a role in limiting its own growth.
We've talked about feedback before. It's how stars influence their environment, right?
Right. As a star grows, it emits increasing amounts of radiation and powerful stellar winds, which can push away surrounding gas and dust, effectively cutting off its own food supply.
So it's almost as if a star's own success in growing can lead to its eventual stagnation. Are there any other theories about what might be influencing this stellar growth limit?
Another fascinating possibility is that magnetic fields play a role. We know that these invisible forces can influence the flow of gas and dust within stellar nurseries.
Right, we talked about how magnetic fields can channel material towards growing massive stars. Could they also be responsible for halting that growth at some point?
That's what researchers are exploring. It's possible that magnetic fields can either aid in channeling material towards a star, accelerating its growth, or disrupt that accretion process, effectively putting the brakes on its growth.
It's like a cosmic tug of war, with gravity and magnetic fields battling for control over the destiny of a star.
That's a great way to think about it. And the strength and orientation of these magnetic fields can vary greatly from one stellar nursery to another, which adds even more complexity to the equation.
So we've got feedback and magnetic fields potentially impacting the mass of a star. What about the very beginning of the process? What triggers that initial collapse of a molecular cloud that kickstarts the entire star formation process?
That's another big question that keeps astronomers up at night. We know gravity is the ultimate driving force behind the collapse, pulling all that gas and dust together, but it's not always strong enough to overcome the outward pressure within the cloud.
So there needs to be something that gives that cloud a nudge, tips the scales in favor of gravity, so to speak.
Exactly. And there are a few prime suspects. One possibility is that shockwaves from supernovae can provide that initial push.
So shockwaves from dying stars that can ripple through space.
The very same. Supernovae are incredibly energetic events. When those shockwaves slam into a nearby molecular cloud, it's like hitting a cosmic reset button. The shockwave compresses the cloud, increasing its density, and that can be enough to trigger the collapse that leads to star formation.
It's amazing to think that the death of a star can actually pave the way for the birth of new stars.
It's a beautiful illustration of the cyclical nature of the cosmos. Another possible trigger is a collision between molecular clouds. Imagine two of these giant clouds bumping into each other in the vastness of space.
Talk about a cosmic fender bender. I'm guessing that wouldn't be a very gentle encounter.
You're right. The collision would create areas of increased density and turbulence, potentially providing the nudge that gravity needs to take over and start forming stars.
So even seemingly random encounters can play a critical role in shaping the universe.
Exactly. And we can't forget about galactic dynamics. The movement of stars and gas within a galaxy, particularly the spiral arms we talked about earlier, can create these density waves that can also trigger star formation.
So it's like a complex choreography with various factors aligning to create the conditions for starbursts.
Precisely. And then there's the question of how environmental factors influence star formation.
Right. It's not like all stellar nurseries are created equal. Some are located in relatively calm regions of a galaxy, while others are situated in much more chaotic and turbulent environments. Does that make a difference?
Absolutely. We're just beginning to understand how these different environments impact the types of stars that form. One factor we're studying is metallicity.
Metallicity. Is that like how much heavy metal music a star listens to?
Not quite, though I'm sure some stars would appreciate a good headbanging session. Metallicity actually refers to the abundance of elements heavier than hydrogen and helium in a star or a nebula.
Okay, that makes more sense. So how does that impact star formation?
Well, stellar nurseries with higher metallicity might have a different mix of elements available to form stars, potentially leading to variations in the types of stars that are born.
So the composition of the nursery can actually influence the characteristics of its stellar offspring. What about those massive stars we talked about earlier? Do they impact their neighbors?
Yes, those massive stars can be quite influential, even disruptive. Their intense radiation and powerful stellar winds can stir up the surrounding gas and dust, potentially hindering the formation of new stars nearby.
It's like they're the rowdy neighbors who keep everyone else on edge.
A very apt analogy. But it's not always a negative influence. Remember, the shock waves from their explosive deaths as supernovae can also trigger new star formation.
Right, it's all about that cosmic balance between creation and destruction.
Exactly. And as we continue to study stellar nurseries, we keep uncovering new layers of complexity and nuance. It's like peeling back the layers of a cosmic onion, only to find another layer underneath.
It's a never-ending quest for knowledge, isn't it?
It certainly is. But despite all the mysteries that still surround stellar nurseries, one thing is clear. They are fundamental to the evolution of galaxies and the universe as we know it.
They're the ultimate cradles of creation, the birthplaces of the stars that light up our night sky. And to think we're all made of star stuff, forged in the hearts of these incredible cosmic nurseries.
It's a humbling and awe-inspiring thought. We are all connected to these vast cosmic processes in ways we're only beginning to understand.
Well said. This has been an incredible journey through the fascinating world of stellar nurseries. Any final thoughts before we wrap up our deep dive?
I think the most important takeaway is that we are still in the early stages of unraveling the secrets of these cosmic wonders. There's so much more to learn, so many more questions to answer.
That's the beauty of science, isn't it? It's a never-ending quest for knowledge and understanding.
Absolutely. And as we continue to explore the universe, I have no doubt that stellar nurseries will continue to amaze and inspire us.
I couldn't agree more. Well, on that note, a huge thank you to all our listeners for joining us on this cosmic adventure. We hope you enjoyed our deep dive into stellar nurseries.
And if you're as fascinated by the universe as we are, be sure to follow and subscribe to Cosmos in a Pod on your favorite podcast app and check out our YouTube channel for more mind-blowing content.
Until next time, keep looking up and never stop wondering about the mysteries of the cosmos.